Hi, now that we have presented the central limit theorem and its derivation, let's show how it connects itself with the previous derivations of the Schrödinger equation. It is somewhat easy to do that because both derivations use the same construct, which is the characteristic function. So, when we was doing the characteristic function derivation, we used only one symbol for the characteristic function, which is the one presented here in the left, and it is depending only on lowercase delta q. Of course, from what we have learned from the central limit theorem, it is now clear that we must use also a different symbol, which is this one, based on capital case delta q. Let's see how we can do that. We know that this one is related to this infinitesimal displacement, while the second z, the capital Z, is related to finite displacements. And the relation between the two, according to what we have seen in the previous video, is just the one we show here, the product of the infinitesimal characteristic functions give the finite characteristic function, because we are assuming that our probabilities are independent. So, using that, we know that the relation between the capital case delta q and the lowercase delta q is mediated by the number n of steps in the summation of the random variable, and when we make n goes to infinity, of course this one is finite, so this small delta q must go to 0, be infinitesimal. Okay, so we may assume here that our previous derivation using the characteristic function was indeed made in terms of this capital case delta q, because while it's finite, as we have seen, it still can be developed up to second order in the expression of the characteristic function. And this is why we can, of course, assume that our first axiom has indeed a usual Fourier transform, and that the characteristic function is no approximation in anyhow. Okay, let's see in a more formally way the connection between the two derivations. We began. Now note that we are using the finite delta q and the capital letter characteristic function. We began with this characteristic function. We have used the axiom. Note that here this is just a usual Fourier transform, and here we have the content of the second axiom. So we have used the fact that psi is a complex function, and so we have written the psi, the probability amplitude, in this way. And when we do that, we develop this product up to second order in delta q, and we get the following result. This was the result that we have obtained in our derivation. But we can also express this result in these terms. This is very interesting to see that can be written this way. And now we can expand this exponential, make the product, and keep terms only up to second order to get exactly this expression here. And we are assuming, of course, that these terms goes to 0 when we make n goes to infinity. So the fact is that this expression, mi, is just the average momentum, of course, in terms of x, and sigma is the delta p squared average. So the fact is that this expression is exactly the expression that we obtain using the central limit theorem to show that for the assumptions that are made in the central limit theorem, the resulting probability density function is indeed a Gaussian. Of course, since we are assuming that we are keeping Q fixed, the point in the configuration space fixed, all these results are related to a Gaussian in P for each value of the variable Q. And this is indeed the way we found our probability density function in our results. So this is quite easy. This is the relation between the two approaches. But it is important to say that then, now, we must include the validity of the central limit theorem into our axioms, because this is what guarantees that we are not making any sort of truncation when we assume that delta Q up to second order is sufficient to our approach. Okay, this is what we were willing to say. Of course, when we have this result, we can just apply the axiom based on the Liouville equation, integrated Liouville equation, to find the Schrödinger equation. So this shows that we indeed have a connection between these two approaches, and this is what we were willing to show. In the next video, I will present the Langevin equations of quantum mechanics, and will represent a huge step into our interpretation of quantum mechanics, because with the Langevin equations we will be able to make simulations of systems, physical systems, quantum physical systems, and we will be able to see with these simulations a lot of the results and the interpretations that we have put forth in the previous videos. Okay, thanks for watching.